So what is momentum? Well, let's define it straight off. It crops up in a lot of GCSEs and IGCSEs, so you may well be familiar with this already, and it'll be a little bit of a recap. Well, the momentum of a body is simply defined as its mass times its velocity, and in symbols that's usually written as momentum is P equals m times v, where m is the mass and v is the velocity. Of course, because velocity is a vector, that means that momentum is also going to be a vector quantity, which means it has direction, and of course that means that it can be represented by an arrow. So it has a magnitude and a direction, like a force or like a velocity or an acceleration. It's a vector. To get a feeling for what momentum is, well, we can see that momentum is big if something's mass is big, or the mass might not be big, but the velocity might be big, or they could both be big. So basically, if something has a big mass or a big velocity, or both, and it has to be moving, it has to have some velocity, then it has a big momentum. So one way of looking at momentum is how difficult it is to stop something. If something has a big momentum, it's not going to be easy to stop. And that could be something with a high velocity, like a bullet, or something with a big mass, like an oil tanker, or something with both, like a running elephant or something like that. So that gives us a sort of feeling of what momentum is. And let's just look at the units of momentum. Well, we can see that because it's mass times velocity, mass is measured in kilograms and velocity is measured in meters per second. So therefore, momentum is going to have units of kilograms, meters per second. Well, having defined what momentum is, we come to something very, very important in physics, the principle of the conservation of momentum, or in this case, of linear momentum, so in a straight line. Well, here it is. It reads as follows. In an isolated system, the initial total momentum of all objects before a collision is equal to the final total momentum of all objects after a collision. Couple of things. Well, firstly, isolated system, what does that mean? Well, it basically means that there are no external forces, so there's nothing outside of the system of just the objects we're considering that's kind of getting in the way and interfering. I'll explain a little bit more when we do some examples. And also, what exactly is a collision? Well, it turns out that this principle is fairly general. Any interaction will actually result in a conservation of momentum. And so that can include things like collisions, but also things like explosions as well. And we'll look at an example of an explosion as well. The proof of this, well, it actually comes from Newton's laws, and we'll look at that in a later video, because it's a bit strange, like, why should this be so? But first of all, the best thing to do is just go ahead and apply it and do some examples. So that's exactly what we're going to do. Okay, so first up, let's look at a collision example. And we're going to take a classic couple of railway carriages trundling along the track, and they're going to collide. Well, the first thing to notice is that we have to watch out for external forces. Friction counts as an external force. So if there was friction acting on the railway, then, well, that would kind of mess up our problem. We're going to have, let's suppose we have the left-hand side carriage moving along at 4 meters per second. And let's suppose the right-hand side one, well, let's suppose that's moving to the left at 2 meters per second. So, well, we also need to know about their masses. So, let's suppose to make it a bit more interesting, that the left-hand side carriage is kind of loaded up a bit more with some stuff so that it has a slightly bigger mass. So let's suppose the left-hand railway carriage is 3,000 kilograms and the right-hand carriage is 2,000 kilograms. Okay, good. So we've got all our information. Now we can kind of see that when they collide, the left-hand side one is kind of going to overwhelm the right-hand side one. And we're going to assume they link together and move off. But just remember that idea again. If there was friction, their velocities would change. They would slow down before they even connected. So that would change the situation. So no external forces also means no friction. So we're ignoring friction. And you'll find that to be the case in these type of examples. Okay, so let's go for it. Let's do our application of the principle. Well, we first need to find then the initial total momentum of all objects. And so the initial total momentum of all objects, I'm going to call P total, and I'll put an I for initial. And well, I've got this left-hand side carriage. Well, MV is going to be 3,000 times 4. And then I've got the right-hand side carriage, which is going to be 2,000 times, well, just watch out here, minus 2. Why is it minus 2? Well, because the carriage is moving to the left, momentum's a vector quantity, remember, so that's quite important. And if I evaluate that, I get 12,000 minus 4,000, I get 8,000 kilograms meters per second. So we've established the total momentum before the collision. So now we need to go after. And I'll just put a note here that let's just write here before. It's always good to clarify in our diagrams, and then after. Well, after, the idea is that they've joined together, they've linked together, and that's important if the question explains that or not, because if they've linked together, they are now one body. And as we've kind of decided, we think they're going to move off to the right at some velocity v, which we need to find. Well, it's obvious here that the left-hand side carriage is going to kind of win the collision, as it were, and because it's heavier and faster, and so that they're both going to move off to the right. But it might not be obvious, and if not, it doesn't matter, because v would just come out negative if it turned out they were actually going to move to the left as a result of the collision. So anyway, we do know in this case, I'm going to put my stuff back in that carriage because that's full of junk. Okay, well, the total momentum after the collision, well, what we know so far is, I'm going to call it P total F for P total final, is that it must be 8,000. We know that because of conservation of momentum. The momentum before the collision equals the momentum after. So we can find the velocity because we know that's equal to the total mass, m total times v, the new velocity of the body. There's no other bodies, and so and the total mass is going to be 5,000, 3,000 plus 2,000. So there we have it. So we get v equals 8,000 divided by 5,000, which gives us 1.6 meters per second. And it's positive, so that confirms that it is to the right, that our object will be moving. So there's a nice classic collision example. So let's have a look at a second example, and this time we will take an explosion. Okay, so well, another classic is two people on an ice skating rink, an ice rink, and they're stationary and then they push each other apart. So the explosion is that action of pushing each other apart. That is a kind of explosion. So it's an interaction. So the principle of conservation of momentum applies. Well, we've got here, let's suppose we've got a bigger person and a small person to make it interesting. So let's suppose we've got a mother and a daughter. So if the mother has mass m mother and the daughter has mass m, well, let's put mg for m girl. Well, at the moment they're stationary, so if I look at the situation before the explosion, well, the total momentum is 0. So I can say P total initial this time is a big 0 because neither of them are moving. After they've pushed each other apart is the idea. So one of them is moving, so mum is now moving to the left and with velocity v mum, and the daughter is moving to the right with velocity vg for v girl. So now we need to look at the momentum after the explosion, so we just need to write a new expression for the total momentum. So P total final. Well, P total final, we know it's going to be 0, but we can write down an expression because it's going to be the momentum of the mum, mass mum v mum, plus the momentum of the girl. Mass girl v girl. And that has to be equal to 0. So that's where it gets interesting, because I can then write, so mass mum v mum plus mass girl v girl equals 0, because the momentum before and after have to be the same, and the momentum before was 0. And I can just rearrange that to get something quite interesting. I can see, or you can just have a scribble, and you can see, well, on the one hand, if I write it up here, we've got that mass mum v mum, the momentum of the mum, is equal to minus the momentum of the girl. So if I just cross the girl's momentum to the other side of the equation, so they have equal and opposite momenta. If I was talking in terms of the magnitudes, well, they would have the same magnitude of momentum. But obviously, because the mum is going in one direction and the girl is going in the other direction, the direction of the momenta is opposite. And so the ratio, interestingly, the velocity of the mum over the velocity of the girl is inverse to the ratio of the masses. And that kind of makes sense. I mean, if we're just looking at the magnitudes, then we can forget about the minus sign. And so we get this really interesting equation, which kind of really makes sense. What it's saying is that the bigger the mass, the smaller the speed, and that kind of makes sense. If you had a really big person and a really small person pushing each other apart, you can imagine the small person is going to shoot off, and the big person is going to move away quite slowly. But that's because the magnitudes of the momenta are actually equal. So it's a nice, interesting example which crops up a few times in questions in various disguises, as we'll see shortly.